Then through that set of attributes, I want to classify that to a discrete set of classes. Right? So let's say I describe a human being by two features or two attributes, the height and weight. Then for a male person, the height and weight will be more. For a female person, height and weight will be less. So male and female, these are two classifiers. Let's say I want to classify the males to normal males and spam males. So I will use certain attributes or certain characteristics to say that this mail is should go into the spam mailbox or it should go to the non-spam mailbox, the normal regular mailbox. So this left side is basically the attributes or characteristics of that pattern, and right side is the class level of that pattern, like spam, non-spam, male, female. So these are the class level. So if I say these are two classes, say I log in into my system. The login could be a normal login, that login could be intuition. So two classes. So like this, if I take the age, marital status, health status, salary status, this will tell me whether a bank can issue a loan or not. If a person is healthy, if a person is of middle age, if a person has a good salary, then possibly it makes sense to use sanction loan for the person. If we have certain inputs, can you drive a vehicle? When you drive a vehicle, you look at your left side, you look at your right side. Say, let's say there is a red signal. You need to press brake. So two classes. I will not be pressing the brake. I will be pressing the brake. The two classes. So if I can do this task automatically, then the system by which I do is called a classifier. And if there are two classes, we call it binary classifier. So this is very standard binary classification. So what is the optimization here? Here, what you do actually is you optimize the error. Say for example, the classification of mails to spam and non-spam. What do? You try to minimize the error. The mails that you put into the normal folder should be all correct. The mails that you put into the spam folder should be all spam mails. So something like this. Let's say I want to recognize the handwritten character for postal codes. So postal codes should be perfectly classified, properly identified. The system should tell me, yes, this is the code number. This is the code of Calcutta, so it should go to Calcutta. So the amount of error should be minimized. Mistakes should be zero. Now, in practical life, for all systems, this is not true. For building such a system, we usually have three phases. First phase is the training phase, next phase is the validation phase, and the last phase is the testing. So training phase is something like in our classroom system, this lecture system. We come and we go to the class and train the system, try to teach the system. The system should learn. So similarly, when I build a classifier, I give certain set of input-output combination. I say, okay, this is character 1, this is character 2, this is character 3. I give an image and I say this is character 1. I give another image, I say this is character 2. So this is how I train the system. And the data that I use is what is called training data. Once the system is built, then we go for checking how good the system is, whether the system has been designed properly or not. So that's what is the validation phase. So phase 1 is training phase. Say for example, you are trying to learn driving. So first you go to the motor vehicle school. The trainer trains you how to do this. Then there is a validation phase. The trainer checks after a couple of days whether you have learned it properly or not. And then you go to the actual test drive where you are given the driving license. So any such classification system will have three phases: training phase, validation phase, and testing phase. This training phase is basically we give a set of patterns, set of examples through which the system should learn. And the second part is validation phase. During this phase, we check whether the system has been trained properly or not. And finally, when some unknown thing comes, you are on the road, whether you can drive a vehicle properly or not. That's the case. So if you have learned it properly, you are expected not to hit anybody. Now maybe you can drive on a road in Mysore, but it may be very difficult to drive on a road of Bangalore. Bangalore is very crowded, congested. So your learning will also depend on the environment. The system that can work in Mysore may not work in Bangalore. So proper training and validation is necessary for designing any and every classifier, right? So let's say these are certain number of patterns and these are the certain attributes, and we say this is a class. And so basically what we have is a kind of learning algorithm. This algorithm does a kind of training through these patterns. Then the model is built, and then we apply the model to test whether some pattern is properly classified or not. Say in South India, we have lots of good quality coffee. So can we have a machine that will automatically uh, distinguish between different categories of coffees? So this is good quality, this is mediocre quality, this is poor quality, and properly it will be like. Say for example, we want to build a system that will automatically classify and tell us, okay, these are oranges and these are apples. These are good quality oranges, these are poor quality oranges. Can we build? Can we build a machine? Can we build a robot that will do it for me? Now, if you will look at this sort of classification is being applied for any and every type of problem nowadays. Say predicting tumor cells, malignancy, classifying credit card transactions, whether it's a normal transaction or fraud transaction, checking your login status, it's a fraud or a kind of unwanted thing or a spam, or you are the legitimate user. You want to classify the protein structure, categorize some news, say whether the news are um, finance related or weather related or entertainment or whatever it is. So all these are types of different classification systems. So by now you must have been clear that a pattern is nothing but a set of features, set of attributes. So any object can be represented by a vector quantity. Right? Like I said, a human being can be represented by body height and body weight. So these are two-dimensional vector that represents a human being. Let's say apple. I can represent with a couple of quantities or attributes or features. Similarly, for orange, I can represent it. The color could be one feature, shape could be another feature. So similarly, any and every pattern can be represented by a set of features or characteristics or attributes or variables. So mathematicians will say, okay, these are variables or coordinates, x1, x2, x3. So x1 corresponds to height, maybe x2 corresponds to weight. So similarly for say handwritten character, 1, 2, 3, this will be represented by certain feature values. What are the feature values? Those are separate issues. So if we have this sort of features, then possibly we can say that we are in some feature space. Then we can play with the mathematics. So now if I say that, okay, I have 10 points where the height value and the weight value are very close. So height is in the x-axis, weight is in the y-axis. So the height is, say, for example, 5 feet 6 inches to 8 inches. Weight is say, around 60 to 70 kilograms. So these points will form a groove. That's a male groove. Similarly, if the height is say 5 feet 3 to 4 inches, to maybe 5 feet to 5 feet 3 inches, weight is say around 50 to 55 kilograms. So those set of points will correspond to the female group. So we can say that the feature space is actually corresponding to a set of patterns, or any and every point in the feature space, or let's say it's in the Euclidean space, will correspond to a class. So basically, some part of this feature space will correspond to one class, another region of the feature space will correspond to the second class. There can be third class, there can be fourth class, and so on and so forth. So basically, we will have a couple of regions in the feature space, which will tell me that these are the classes. And I can draw a kind of boundary between these two groups. Now, this boundary is nothing but the classifier. Now, basically, the question will be, how do you design this boundary? So in terms of optimization, in terms of mathematics, classification is nothing but a generation of a boundary between two sets of patterns, two groups of patterns. And of course, we will try to minimize the error. such that the classification or grouping is 100% perfect. Let's say I have these two sets of patterns. So this red corresponds to one group, blue corresponds to the other group. So can this be the separator? So this is the classifier. It's a linear classifier. I can have a non-linear classifier also. So if I assume that there is a linear boundary between the two, then I will say that all points for which this quantity is positive, they belong to one group. And for all points where this quantity is less than 0, corresponds to the other group. So this is my class 1, this is my class 2. Now my job would be to find out this decision boundary. Determination of this decision boundary is the classification. So how good is this classification? How can I generate this? What I will be given? I will be given these training points, this pattern. Okay, this corresponds to class 1, this corresponds to class 1, this corresponds to class 2, this corresponds to class 2, and so on and so forth. Now you can see, being mathematician, you can as well imagine that you can have infinite number of lines between these two sets of patterns. Which of these sets is the best classifier, is the best line to distinguish these two groups? So that's what is the job of pattern classification, and that can be done by many ways. Right? This can be a classifier, this can be a classifier, this can be a classifier. Infinite number of classifiers I can design. Which one of these good? Which one of these poor? Which one of them is bad? Which one of them should I choose? These are the issues that actually will be taught in this lecture. So I will initially tell you a couple of classifiers which are not really that good. Then I will go to a classifier that's a very good classifier. Okay, so for mathematicians, now it should be clear that classification is nothing but a generation of a decision boundary between these two groups or these two classes. Do note that these points are given to us. That is the training phase. The points means these are what is called training pattern. That means that I am given a set of patterns which I know that which class it belongs to. And it will say that, okay, this is point number 1 and this belongs to class 1. This is point number 2 and this belongs to class 2, and so on and so forth. Now, how will I generate a decision boundary between these two? I'll talk about 3 classifiers. One very simple, one little bit of adaptive, and the final one, what was the task of me, that is to SVM, support vector machines. Okay, so this is a minimum distance classifier. That's the simplest possible classifier one can think of. So how do you design this classifier? How do you define this classifier? The rule is very simple. The rule is something like that. You find out the mean vector of these two groups separately. This is for class 1. Find out the mean of the class 1. Find out the mean of class 2. So this is the mean of class 1. It's the mean of class 2. So I assume that this mean vector actually represents the class. I had 100 patterns. I have found out the average. These patterns could be in any dimension, mind that. I'm showing you it in 2 dimension because of simplicity. It could be in any dimension. You can have any number of features. So this mean is the representation of class 1. This mean is the representation of class 2. Now comes a third pattern, test pattern. I find out the distance of these patterns from these two mean values. And whichever is the smallest, I say that this test pattern belongs to that group. So like this distance is less than this distance. So I will say that this pattern belongs to class number 1. Since this is based, the decision is taken based on this minimum distance, I said it's a minimum distance classifier. So this is the rule, this is the intuition, that whichever is the nearest, I classify to that. Whichever is the farthest, I classify to, I don't classify to that. It's a very simple case. So this is the intuition, this is the logic. What's the mathematics behind? Now if you do the mathematics, you will see that the boundary for this sort of rule is nothing but the perpendicular bisector of these two, perpendicular bisector of the line joining these two mean values. So if I do the mathematics, you will see that the classifier for this particular logic is nothing but the perpendicular bisector of the line which joins this mean and this mean points. How do you get it? So you find out the mean value of each of the classes, and there is a new pattern. Assign that pattern to the class omega or C1, C, whatever it is, if this distance is the minimum. So I can apply it for any number of classes. If I have 10 classes, my what is it called? This subscript will vary from 1 to 10. So there will be 10 minimum points, and there will be 1 point from where I will find out the distance of all these 10 minimum. So whichever is the minimum, I will assign to that particular class. Now, if you do the mathematics, you will see that this corresponds to a line, the boundary or the classifier corresponds to a line which is nothing but the perpendicular bisector of these two, of the line joining these two mean values. Right? So this line, the classification or classifier is now fixed. I have no control over that. Once I use that logic, minimum distance, the perpendicular bisector is the fixed classifier. So that may be a good classifier, may not be a good classifier. Now, if you notice these, that I have these blue points, I have the red points, the perpendicular bisector looks like this. Now, let us say that I have two classes. I have two class. One is a very big class, say poor people in India. It's a second class, rich people in India. Then how will the perpendicular bisector look like? This is my perpendicular bisector. Now this perpendicular bisector means all points to the left of this side is nothing but class 1, the rich class. But that's not true. This is an error. Boundary should have been in between these two, but not. So this classifier has many limitations. The error is not minimum. Error is not very small. If this big class actually eats up the smaller class. Similarly, if I have two set of points like this, then the classifier, how will it look like? It's something like this. This boundary is not actually making any mistake for these points, but if some pattern comes from here, it will be classified to the right side. But practically, this is very close to this. So it should have been here. So the question boils down to, how do I design a good quality classifier? How do I design a good quality classifier? Is this a good quality classifier? Surely no, but it's a very simple classifier. Designing this classifier for two classes is very simple. You find out the mean values of the two groups and draw a perpendicular bisector of the line joining these two. Then if you use the Pythagorean theorem, you will see that any point to the left of this will belong to class number 1. Any point to the right of this will correspond to class 2. And the logic will be valid. All points to the left of this line will have minimum distance from the center of class 1, and all points to the right side of this will have minimum distance from the mean of class 2. That was very simple, but the accuracy, the optimum value, the optimization that we are looking for, that okay, we want to have a minimum error case, it's not so good. So this can be a classifier, but may not be a good classifier. So practically, this is insensitive to variance of the noise, variance of the categories. Noise will actually affect a lot. Since we are actually taking the arithmetic mean, the effect of noise will be too much. So this may not be a good classifier. So this is for, general expression for that, the same thing, whatever I have shown you in the previous slide. I am not just solving this. This was the equation of the line. So this may not be a good classifier. Instead of two classes, if I have multiple classes, then what I will do is pairwise and pairwise bisector. So this will be class 1, this will be class 2, this will be class 3, class 4, class 5, and so on and so forth. So I can design a minimum distance classifier for any and every number of classes. But the boundary remains fixed. Boundary depends completely on the training set and is nothing but the perpendicular bisector of the line joining the mean values of the classes. I will take them pairwise. So the point is this could have been a classifier, but the case is this actually makes this boundary fixed, makes the classifier fixed. I have no control. I cannot shape this. Even if I want a classifier that may pass through somewhere here in between these two groups, I cannot do that. So this was not that much popular. Although we have it, we use it. Simply, it's not so popular. So people wanted to go for a better classifier. Let's say this is a kind of neural network based classifier. I'll not go into the neural network part. To mathematicians, what is needed, I will tell you. Let's say I have these patterns x and y, rather the feature values x and y, two features, two attributes or two variables. So w1x plus w2y greater than equal to certain value of theta, I will say it belongs to class number 1, else it will belong to class number 2. Right? Let's say x corresponds to marks in mathematics, y corresponds to marks in physics. So I make a weighted addition, weighted sum of these two marks. And I say if this weighted sum is more than certain value of theta, then I will admit the student to this SGSL. Else, I will not get it admitted to this college. Very simple case. That x is marks in mathematics, y is marks in physics. I make a weighted combination w1x, w2y, and I say if the total, the weighted sum is more than certain threshold value, I will get it admitted to my college, else I will not. Now, as a mathematician, you know that w1x plus w2y is equal to theta corresponds to a line. So what does this mean? This classifier means if the total input is more than that, so that point will come from this group on one side of the line. Else it will come from the other side of the line. So this can be a kind of classifier again. It's not like that minimum distance classifier. It's a separate type of classifier. This type of classifier is present in our brain, human brain. That's why it's called neural classifier. We do classify like this. We actually make an weighted addition or weighted sum of the feature values, and based on certain threshold, we decide whether it should be classified classified to group number 1 or it should be classified to group number 2. So x and y are two feature values or characters. Do note that although I'm saying x, y, these are two features, in general, my discussion is valid for any and every dimension. Just in 2 dimension, I am showing this because it's easier to show. Any dimension, it is valid. In 2 dimension, it would be a line. In 3 dimension, it will be a plane. In higher dimension, this will be hyperplane. So the equation remains the same, ax plus by plus c equal to 0, or ax plus by plus cz plus d equal to 0, and so on and so forth. So now here you will see that the decision boundary between these two classes is w1x plus w2y is equal to theta. Now the point is, I can vary this w1, w2 and theta. If I can vary this, I can vary the position of the line. All of you are mathematicians, so you understand that. If I vary the position of w1x plus w1 plus w2 and theta, then I can change the position of the line. So like the minimum distance classifier where the boundary was fixed, I had no control. Here I have control. I can modify this w1, w2 and theta to change the position of this line. And how can I modify this? That rule is again fixed. I can change the w and theta using this equation. This equation has two parts. Part 1 is proportional to the error that I make. If my pattern is properly classified, I don't do anything. If the pattern is not properly classified, then I change the w value. Right? And x is the input. So I give an input x. I notice whether that input is properly classified or not, if there is any error in classification or not. If there is any error, then I modify the weight values proportional to the product of the error and the input value. And eta is my proportionality constant. This is what is called learning rate. It depends upon person to person. All of you are listening my lecture, but it's not true that all of you are learning by the same amount. Different people are learning by different amount. So that constant depends upon your ability, your previous background, your previous knowledge, and other things. So that will determine the eta value. Rest two are fixed. So the learning amount of learning or change in weight is proportional to the error as well as the input value. So proportional to the product of this, directly proportional, and eta is the proportionality constant. Now there is a mathematical rule that even if I start with a random value of W1, W2, and theta, I can get a good line. What is a good line? I will show you in the next slide. I can get a good line that in finite steps. So that means I can modify the W1, W2, and theta values in such a way that finally the position of the line will be in between these two groups, and that will be a very nice position. May not be the best position. I'm not claiming that will be the best position. It will be a good position, I am saying, and that will pass in between these two classes. This can be mathematically proved. I'm not going into the proof, but you can assume that this can be proved, that yes, I can get a classifier like this. So I can say that this classifier is better than the previous one, because for the previous one I had no control over the position of the line. The position of the line got fixed once I give the training patterns. But this particular case, I can modify the position of the line by modifying the values of W1 and W2. How do I modify? I give an input pattern and I check whether the pattern is correctly classified or not. If not, I modify the weight. If not, I modify the weight. I give one more pattern and do the same job. So this way I go on changing the position, and it can be mathematically guaranteed that even if I start from this where the error is very high, this will gradually oscillate. It will move. With change of time, I give input pattern, input pattern, input pattern, correct and correct, correct. So this is what we do in the class. First time we come into the class, we teach something, the students don't learn much. Then next time we come, give some more input, the students modify. Some more input, students modify. Some more input, and maybe towards the end of the semester, the perfection comes off. So this sort of classifier is present in our brain. And I can simply say that this is a better classifier than the previous one, because here at least I can design the position of the line. I can determine the position of the line. And the mathematical proof exists which says that yes, a line passing through these two classes can be obtained through this. Now, do note that this line may not be the best line. This will be a line that passes through the in between the classes, through this vacant space. But maybe somewhere very close to this group, maybe close to this group, maybe at the middle, anywhere in between. I have no control over that. Now, can we have something better than this? And that is what is support vector mesh. So this was the flow of discovery of support vector mesh. We want to do a kind of classification, and we assume that the boundary is linear. This was an assumption that the boundary is linear. So then we had this minimum distance classifier, which was very bad. Then we had this neural classifier, which is somewhere in between. Then people thought, okay, this may not be the best boundary. Let us try to have a good boundary, a better boundary, the best boundary. And that's what gave rise to something what is called SVM, or support vector meshes. Okay, so the perceptron can be used to find one such boundary. May not be the best. So I can find out a boundary like this. I can find out a boundary like this. I can find out a boundary like this. Maybe this. Maybe something like this. Maybe something like this. So this way the search went on, and they said that okay, if I have a classifier, this dotted line is the classifier. Here is the classifier. If I have a classifier like this, which is more or less equidistant from these two boundary points, then possibly that is a better classifier, right? Look at this. This bound, this is the classifier dotted line. This is somewhere very close to this class. It is little farther, okay, but not equidistant. These are two equidistant lines. I can still move farther. You see that these three lines are parallel. This is my classifier. This is a line parallel to this line and is passing through this point, which is the boundary point of class 2, and passing through this point, which is the boundary point of this. So this is the margin. This is what is called the margin. This is what is the flexibility that I have, because I could have passed this dotted classifier through anywhere. So if this dotted classifier is the line equidistant from these two lines and is parallel to this, then that is what becomes a support vector mesh. And since this distance is maximum, it's called a maximum margin classifier. So the people who are working on SVM, support vector machine, they are trying to determine this maximum margin classifier. What is the advantage? Advantage is this classifier will have flexibility on both these sides. So this class number 2 could be expanded from here to here. Class number 1 could be expanded from this leftmost line to this. So this is the generalization capacity. If I have a boundary like this, that could be something overfit to class number 1. If I have a boundary somewhere very close to class 2, that could be an overfit to class 2. But this could be something where I have more generalization capability. So this was the intuition. That yes, I want to have something like this. Now, how do you do this? That's what is the mathematics, and that's what is support vector machine. So this line, this dotted line is the classifier, which is equidistant from these two lines, these two classes, or boundary points of these two classes, or basically this point and this point, they are called support vectors. They are supporting these vectors. Each of them is a vector. It's in 2 dimension or 3 dimension or 4 dimension. I call it, pattern mathematicians will say it a vector. So these are the support vectors. These vectors actually support the decision making process. So it's called a support vector machine. So this classifier is the support vector machine, and that's what people are trying to do. So in SVM, the job is to design a classifier like this, boundary like this, a line in 2 dimension, a plane in 3 dimension, and hyperplane in other dimensions, higher dimensions, such that that will distinguish the two groups and will be equidistant from the two classes. Or in other words, they will have maximum margin. The margin is this, the distance between these two yellow lines. This is the margin. So this margin is the maximum that we can get given these patterns. These patterns are the training patterns. So that's what is called a support vector machine. Now, in due course, I will try to show you in another half an hour or so how to get such a classifier, how to have a boundary with mathematical proof that yes, this is what you can determine. Okay, so these points are called support vectors. This is supporting the decision making process. So what are support vectors? They are actually the boundary points of the classes, boundary training patterns of the classes. And this is the optimal hyperplane of that support vector machine. And this margin is what is the margin of this classifier. And NPM tries to find out the hyperplane that maximizes this particular margin. This is a support vector, this is a support vector, this is a vector. So the point will be like minimum distance, we needed all the training patterns. Here, I will not need all the training patterns. I will need only a couple of training patterns, which are nothing but support vectors. So maybe just these 3 points would be fair enough to design my classifier. I will not take the help of this. So that's why these 3 will be called as support vectors. Now, why people suddenly went for that? Why they wanted to have this maximum margin classifier? Because these sort of things will have their power. Power of what? Power of classifying properly. Power of reducing error. Okay. So the classifier number one, that's minimum distance scale, does not have good power. Power of classifying unknown patterns properly. Similarly, neural classifiers also do not have that sort of power. But SVM has more power. So that's what we will be explaining in due course. So more power means this can model more complex classifiers. And less power means not going to overfit but restricted in what it can model. Like minimum distance classifier, it could not model anything, just two classes where one was having more variance than the other, it could not handle. But SVM can do, neural classifier could do, right? But in such a case, the boundary may be an overfit. Overfit is what? It's very close to one class. So whatever you have taught, the student has learned just that. There's no flexibility. There is no generalization ability. That's not desirable. You have to have generalization ability. The student should be in a position to do something more, right? So how do you actually model this? With training error, test error, and other things. Training error is what? We have given a set of training patterns. How much is the error? If all the training patterns are classified correctly, and then there's no error. Okay. So how do you measure error? Y is the actual output, and this is the output that is given by your classifier. So the absolute distance, absolute difference is the error, whether it's classified properly or not. So for a training set, I know the number of pattern, so I can compute the error, just addition. And it's a half is taken just for some, what is it called, normalization. So if I have R number of training patterns, 1 by R into this. So this is nothing but the fraction of training patterns, not classified properly. And similarly, for unknown patterns, I cannot compute this with added evidence, so I go for an expectation. So this is the probability of misclassification. Okay, so these measurements, we are assuming that my classifier is F, my machine is F, under the assumption that all training points are drawn from same distribution and the test patterns will also be drawn from the same distribution. So this is the underlying assumption. Otherwise, if I train a system on, say, human being and try to test it on some animal, it will never work. Say height and weight I talked about. So the training pattern, test pattern, validation pattern, all of them should come from a same distribution, similar distribution, right? So these are basically that IID and other things, whatever we require. They should come from the same distribution. Okay. So this is basically the model parameter. And how can we actually reduce this? Because training error we have under control. We know the training pattern. Test error we do not have. So these are the two people actually who did this job, all this mathematics, Vapnik and Chervonenkis. They told us something what is called VC dimension, wherefrom we can determine the power of this machine. You can see that the power of a machine is very high. Power of this is very high because the relation, this particular relationship holds. I can compute the training error because I have the training patterns with me. So if I have the training pattern and I know something what is called the VC dimension of this classifier, then I compute what could be the bound of this test error. So that is the power, that I know how much error I am going to make for such a good classifier like SVM. This is not possible for all classifiers. So how much is that test error I am going to make? That's very important. In future, how much error I am going to make? If a student can find out, yes, in semester how much error I am going to make, then that will be great. So this has a relation like this, where H is the BC dimension of that particular classifier. What is BC dimension? That I will be telling you in the next slide. Okay, so estimate of the upper bound of the error. So what is the VC dimension? That's what we are going to this. VC dimension, for determining VC dimension, it needs shattering. You may be knowing shattering means dividing into classes. Say I have 2 points. These 2 points I can distinguish into 2 groups using one line, right? The line could be maybe 2 points could be in class number 2, or 2 points could be in class number 1. This point could be in class number 2 and this one 1, or this is in 2 and this. So this 2 to the power 2, 4 possible combinations could be there. And just by using one line, I can group them. Either I can put all of them in class number 1, or all of them in class number 2, or one in class 1, other one class 2, or the other one class 1, the first one class 2. So just using one line, I can make all possible dichotomization of 2 points. So this is what is called shattering. So I can shatter the points, 2 points, using a single line. But can I do it for 3 points just by using a single line? Maybe no. Maybe no. So for this particular case, I cannot have it. So 3 points I cannot shatter using just a single line on 2-dimensional space. But maybe I can do that using 2-dimensional vectors, or 2-dimensional, what is it called, plane. Just by using one line, I cannot shatter them, but maybe I can do that using a plane. So using a plane, I can shatter 3 points. All possible ways I can do it. So similarly, can I do just using one plane 4 points? Can I shatter 4 points using one plane? No. It's a problem of XOR. I cannot shatter this. I cannot classify this. So maybe a linear boundary does not exist. A single plane cannot help me. Right? So if I can do that completely, that shattering, then that actually gives us an idea about the VC dimension. So practically, d plus 1, if d is the dimension, d plus 1 is more or less, may not be the perfect value. I'll show you the perfect value of which is dimension. Most of the cases, d plus 1 is the VC dimension. So number of parameters that you actually have in d dimension is d plus 1. So this d plus 1 is a kind of estimate of the VC dimension, but may not be the actual value exists, actual mathematical expression exists, and I will show you that. But in many cases, this is d plus 1. Okay, so if you have d dimension, you can shatter d plus 1 points. Let's say I want to have a circular boundary. Maybe all the 3 points I can put in all possible ways, right? All of them in one red group, one red group, 2 red group. So this way, if you look at that, you will see that 2 to the power 3 possible combinations are there, and that can be generated by this circular boundary. Not a linear boundary, circular boundary. But can I do that using 4 points? No. Even using a circular boundary, we cannot do that. So for 2-dimensional patterns, the VC dimension is 3 because we can maximum shatter 3 points. So these are the possible dichotomies, right? They're just for 3 patterns. All 3 patterns on this group, 2 patterns on this side, these 2 patterns on this side. So this way, you'll see that these are the different possible dichotomies and different amount of margin. This is a good margin. It's a good margin. These are very poor margins. So which classifier is the best? That's what you need to understand. Okay. So the VC dimension is practically greater than equal to M. M-dimensional space. The VC dimension is greater than equal to M. It's not always M plus 1, it's greater than equal to M. And I think there is an expression somewhere. And this M is actually not the number of parameters. These are nothing but the number of parameters which actually affect the system. That's for engineers. How many parameters actually affect? So that's what is the case. Right? So using this VC dimension, I can say that, okay, how much is the power of the system? Is it the number of parameters? No, it's not the number that actually affects. So this VC dimension will be more than equal to M, so that the M patterns, M points can be shattered. If you can shatter M points, then we say that the VC dimension is something more than M in any dimension. Okay. Now I will come to the real mathematics of SVM, how actually we do this. As I have already told you, that these are the support vectors. And say I have a pattern X. The distance from this is W transpose X plus B over mod of W. And that's a very standard norm, it's a perpendicular distance. So standard distance for any point, and every point is this. And the margin is the rho. Margin is this gap. Okay. So this shows that the margin is actually dependent on the support vector. This I have already told you. So it does not depend on any other vectors. Okay. Now let us take this as standard two-class classification case. So I can have a boundary set like this. I can have a margin like this. Maximum margin provides a room for adjustment or flexibility, generalization. So room for adjustment because these patterns can be moved from this other. The more reliable, more generalizable. Okay. So this is what is the expression for H. H is less than equal to this. D square over rho square and M0. M0 is the that dimension. Okay. So this H is bounded above. So it's dependent upon the number of, sorry, not dimension, the number of patterns it can shatter, or the radius of the circle and the margin. Diameter of the smaller square that can include all the training examples. I have shown you in that circular shape. So that diameter of that circle was D, and rho is the margin. So D square by rho square or M0, minimum of that plus 1, that's the BC dimension. So this has been proved mathematically by Vapnik. Right? So this is the power that yes, I know the VC dimension. So if I use the maximum margin, so I can predict something. So mathematically it's very powerful. Other classifiers are not mathematically that much powerful. Right? So intuitively this implies that regardless of the dimensionality M0, we can minimize the VC dimension by maximizing the margin. And this I have no control. This is the dimension. M0 is the dimension. I have no control over M0. So since I'm taking minimum of these two, by maximizing these, I will have a control over the BC dimension. So if you have a lower BC dimension, the power is more. So that is why people are going for maximum margin classifier. Okay. Now the complexity of the classifier is kept less regardless of the dimensionality. So this is the beauty of SVM. The other classifiers do not have it, and this is why this classifier or SVM is more popular to the mathematicians, because mathematically it makes more sense. Now how do you get that? That's what I am going to tell you now. That how do you get this maximum margin? Okay, let us assume that the optimal hyperplane has an equation like this. General equation Ax plus b equal to 0 of line. So A will be line in 2 dimension, it will be a plane in 3 dimension, and a hyperplane in hyperdimension. So this is basically is a hyperplane that divides the space into 2 parts, right? So how do I find this? W vector, you as of you know that this actually determines the position of the line of the hyperplane in dimensional space, and the bias represents the shift. So how do I find out? If you remember correctly, sir, all patterns to the right of this line is in one group, all patterns to the left of this group is another class. So g of x is greater than this means indicates class number 1, less than this indicates class number 2. So we need to find out the weight vector and bias vector such that there is no classification error. Now, instead of getting this, so this will tell me the class which is to the right. So if I want to have a margin, say that rho or v or whatever it is, this will be more than that v. If I want to have a margin in one side, right? So v on two sides will be like this. So distance x from the perpendicular plane is w1x plus b divided by mod of w. And if this distance is greater than equal to v, so this shows wx plus b is greater than equal to v into this. So if my one class is plus 1, another class is minus 1. So this is greater than equal to plus 1. This is greater than is less than equal to minus 1. So these are the two boundary separators for belonging to class number 1 and class number 2. One class is represented by plus 1 and the class is represented by minus 1 because of simplicity of mathematical formulation. Usually we say one class 1, another class 0, but for this particular case it's one class is 1, another class is minus 1 because this will help us to simplify the mathematics. Okay, so w1x plus b greater than equal to 1 means output is 1, that corresponds to the plus class, else corresponds to the minus class. Now since this is minus 1 plus 1, this I actually can combine, that this is the plus 1 into this greater than equal to this, or minus 1 into this was minus less than equal to minus 1, that becomes again plus 1 because this is minus. So that is the reason why it is taken as plus 1 and minus 1. Yi into this is greater than equal to 1. So this is my classification. And for the support vectors which are on the line, so this will be equal to 1. So this is the support vector construct. So those two boundary lines for support vector, this is equal to 1. For all non-support vector points to the right, it's greater than 1. To the left, is less than minus 1. Or that can be written as a general equation like this. Oh God, it mixed up. So maybe I change the machine. But it's the same thing. W1x plus b is less than equal to, I am assuming that margin to be rho. It's rho by 2 on this side, rho by 2 that side. So this rho by 2 this side and rho by 2 that side basically is nothing but the double of the distance. So this is actually boiling down to the difference between those two. The difference of this, the margin. Margin is actually y into this, okay, w x plus b over mod of this. Then another point by mod of this, if we subtract these two, this comes out to be 2 over mod of w. So the margin or the distance between these two parallel lines is rho, and that's equal to twice the perpendicular distance, and that's equal to 2 by mod of w. So basically, we will have to maximize this under certain constraints. So this is the problem of support vector meshing. Maximize this margin under certain constraints. Okay. So this is nothing but maximizing this value under certain constraints. So constraints are what? It has to pass through those boundary points as support vectors. So those are the linear constraints. So basically, it's nothing but a quadratic optimization problem with one lone class of mathematical issues having linear constraints. So it's a quadratic optimization problem that can be solved very simply using Lagrange multipliers. All of us know, all mathematicians know that yes, I can solve this quadratic optimization problem with linear constant. So SVM determination of the maximum margin classification boils down to the fact that it's nothing but optimization of a quadratic function subject to certain linear constraints. So I can use a kind of mathematical programming for this, any quadratic optimization problem. most popular case that we use in SVM is what is that? Lagrange multiplier with KKT condition and other things, right? So this way, given a solution of this for this Lagrange multiplier problem, we can solve this. I'm not going into the detailed evaluation of this function. So this is how you get the W value. This is how you get the expression of B if you solve that quadratic optimization problem using Lagrange multiplier. So expression for W will be this, expression for B will be this. So once you know the W and B, you know the position of the lines. You know where is the support vector. You know what is the margin. So all non-zero alpha indicate that this is a support vector, because that will be the constraint, right? So for all non-zero alpha i's, this will correspond to the support vector. So determination of the support vectors is very simple using this Lagrange multiplier, and determination of the classifier is also very simple like this. So this is my classifier, where you can see that you do not need the weight values directly. What you need is the dot product or inner product of certain number of vectors. You need the inner product of the vectors and the support vector and the unknown test pattern. So you do not need a whole W. Now the number of support vectors is very less. So that shows the complexity in computation of the classifier will be pretty less, because it will depend only on the support vectors, not on any other point. All other classifiers will require all the training patterns. So basically, this will rely on the inner product or dot product of the test pattern X and the support vectors. Nothing else. You don't need the actual W also. Just B and this. So the important part was here that how do you solve this equation? You find out this maximum margin using the Lagrangian multiplier or any other mathematical programming you feel like you can go for. So it's nothing but quadratic function optimization with linear constraints. Any and every topic you can go for that. Doesn't matter. Okay, so the final classifier looks like this. So this is my support vector machine. The line. So once I know this line, determination of the corresponding other two lines is very simple. Right? Now, by now you have realized that what we have actually done is basically we are assuming that okay, my points are good, they are linearly classified, and I am trying to find out a maximum margin classifier that will pass through these two groups. But real life is not so simple. Real life is a little different. In real life, what happens is the data points are like this. These are the training patterns. So it's a mixed stuff. This is one class, this is another class. So such a classifier is not going to work. It's a very powerful classifier, but it's not going to work. So what is the use of such an SVM, although mathematically very strong? What if the training set is noisy? That's a real life case. So training set is noisy. So there are a couple of solutions to this, and those are real life things. This is where actually you need to do something. So this is what is called overfitting. Boundary is something like this. But that's not useful. It's poor. There is no generalization. So what you do is you give some flexibility that yes, I don't want 100% correct classification. I don't want zero error during my designing phase. Let there be certain errors. What are those erroneous points? Those could be outlier points. Those could be extreme points. They may not represent the class properly. Like say, salary of Mukesh Ambani. That cannot be considered as a good point, even if it's a rich class. So rich people in India, Mukesh Ambani could be an exception. So that points should not be considered. Let us give more flexibility. Let us say that is an erroneous point and we'll keep it inside. This boundary will not be here. Boundary will be somewhere here, where this point will be inside this boundary. That will be misclassified, I know. Deliberately, I am introducing that error such that the test error is less. Generalization capacity is very less. So what I am doing is, for each and every pattern, I am giving some amount of penalty if it is not properly classified. So that's what is the slack variable. This is a kind of mistake I am allowing. That yes, it should not be very hard. I give a little bit of flexibility over this. Now, this is a kind of penalty. If it is misclassified, the amount of penalty is something like this. So I will be optimizing this rather than only this W by 2. Hard classifier, that's what we discussed until now. This was optimization of this. But I will say, no, I don't want to minimize this. I want to minimize this whole thing. I will introduce a certain amount of error so that then the boundary is not a very hard boundary. Boundary is not something like this, not overfit. It will have certain kinds of flexibility. Okay. So this is what is called a soft margin classifier, and this is a very popular classifier. Then rather than using a hard margin, I will use a soft margin. So what will happen is this will be a minimization of this. This is the hard case, minimization of this, and the soft case, minimization of this plus this. Right? This is minimized for all given patterns, all training patterns. So remember that this boundary is not going to have the minimum error for all training patterns. So this will nothing but a way of controlling the overfitting. Just to avoid overfitting, I am making some mistakes deliberately in the training phase such that error in the testing phase is reduced. Because in a real life case, data set is not so simple. Data set is very complex. A data set is something like this. Some points come, this red group and blue group, they're intermixed. So rather than hard margin, I can have soft margin. So that's one solution. I can go for something else also. That's what is called non-linear supervector machine. By very nature, SVM is linear because we are determining the equation of the line or plane or whatever it is. W transpose X plus B is equal to B. So instead of that, we can use something else. We can use something in non-linear classifier using some other trick. That's what is referred to as kernel trick. Right? Let's say these patterns are given a transformation x squared. Then the pattern set becomes like this. Then possibly a simple linear classifier will work. The boundary is changed. So this transformation of this pattern set from here to here is what is called kernel. I use some mathematical function to transform the input space from this to this. The aim is in the transform domain, my classification ability will be more. The patterns will become more linearly separable. Then the question will be, how do I choose this particular kernel? How do I give this transformation? How do I handle this? So like here, time. So particular case, I have given just square transformation, but it may not be the square transformation. It could be something else. What is that transformation? So that is the general idea of nonlinear support vector machine, that this input feature space I transform to a newer space using some function. What function? I will tell you. That's practically a kernel function. So if I use a kernel function, I save some time for some other purposes. That's why you use a kind of kernel function to transform it from this to that. So you see, it's not linearly separable in this place, but this is linearly separable. I can just use a plane to distinguish these. So how do I choose this transfer function phi? So nonlinear SVM actually is nothing but applying some kernel to transform the input space to another space and apply the simple linear SVM there. So actually there is no nonlinearity. You are transporting the input space to some other space so that it becomes linearly separable. Most of the cases we are transforming it into a higher dimension, mapping it into a higher dimension. Nowadays you have seen that deep learning is very popular. Deep learning is what? The same job. Transforming the space, input space. Solution technology is not changing. What is changing is the transformation of the problem from one domain to another domain, another domain to another domain, such that the problems becomes solvable, simply solvable. So kernel trick is also that this phi function is a kernel function. All functions are not kernel functions. Kernels will have certain characteristics. And this particular case, you have seen that this actually needs a kind of, what is that? Inner product. This is a kind of inner product. So if I can have a function where this inner product will be automatically computed, that could be used as my transfer function phi. Then I will save a lot of time because that multiplication is already needed for my SVM. So if that is computed somewhere, so that is why this nonlinear SVM or kernel trick with SVM comes together, because inbuilt is there that it is a kind of nonlinear transformation or a kind of dot product is needed, inner product is needed. Okay. So let's say this is my kernel function, the linear classifier as an inner product, that is, you have seen the transport into X. So if I can design this function to be a dot product of these two, then my life becomes very familiar. Okay, so a kernel function is a function that is equivalent to an inner product in some feature space. So all functions will not satisfy this property, only a couple of functions. Only those functions which will satisfy these particular properties, that k of xy is equal to phi of x transpose into phi of x, because that transpose and that is required over here, then possibly that will be very much useful. Okay, so that's a very simple case. I have the vector x, which has two components, and then kx y is equal to 1 plus x transpose x whole square. Then you will see that rather than computing so many terms of this, I can just simply say that kx is this, ky is this, and this is my product. I don't need to compute so many. So that's a kernel function implicitly maps data to a higher dimensional space without the need of computation of each phi x. I don't need to find out this. Right? I use this kernel, so this product is automatically determined. So some such functions, if I can choose, then my life would be very simple. I will have a nonlinear support vector machine and do the job. And this kernel function will satisfy certain properties following the Mercer's theorem, that there should be every semi-positive and definite symmetric function is a kernel function. This can be proved. And for mathematicians, this is very important. That is, every semi-positive definite symmetric function is a kernel function. For engineers or computer scientists, that could be taken as a granted thing. What they need is some functions where these properties are satisfied should be fair enough. Okay. So what are these? So different kernel functions can be chosen. Most very simple Gaussian function is chosen to be one of the kernel, very popular Gaussian kernel, because here the dimension is infinite. The space in which you map this is infinite. Okay. Now once you are in higher dimension, your separability increases. So 1 plus x transpose p to the power p is a kind of polynomial kernel. This is a kind of Gaussian kernel. So there can be plenty. We don't need this. Any and every kernel may not work for any and every problem. So you need to find out a good property or good kernel for your job.
Sir, screen is not visible, sir.
Screen is not visible now?
Yes, sir. It is not visible, sir.
Okay, let me reshare. Okay, so the kernel trick I can apply to handle nonlinear problems. Nonlinear problem means problem where the classification boundary are nonlinear. So here what we are doing, using some kernel function to transform the input space to an output space where the linear separability works, right? So if you look at the properties of support vector machine, there is flexibility in choosing a similarity function, sparseness of solution when dealing with large data sets because you need only the support vectors, you don't need the whole data set. Ability to handle large feature space because the dimension is not of so much importance considering the BC dimension. Dimension will not matter much. BC dimension is lower bound and the dimension. And overfitting can be controlled by soft merging. Overfitting can be controlled by soft merging, or even we can go for nonlinear transformation or kernel trick. And it has very simple mathematical properties, nice mathematical properties. It's a very simple convex optimization problem, quadratic optimization problem with linear constants where the convergence is guaranteed, right? And you, even by default, you know how many parameters are important. So which features are important, which characteristics are important. If you look at the application, plenty, not 1, 2, 3. 10, 20, 100, any and every field, you will see that SVMs are becoming much more powerful. If you are a computer scientist, you need a digital version of this sort of optimization algorithm, then SMO is very popular. So tuning this SVM using what sort of kernel, or what sort of transformation function, or what sort of merging and other things, there are plenty of flexibility, and you can do kind of research on that. So this is why SVM is very popular when you are trying to deal with large dimension, because it's not completely dependent upon the dimension. It has other parameters which controls the power of this. Okay. Drawbacks. It's very sensitive to noise. I have already told you. That's why that slag variable is well introduced, and to go for a soft margin. So be very careful. Noise pattern in the training phase is very critical for designing SVM. As I told you, this Mukesh Ambani's salary, that could be a noise pattern. So need to be very careful about the training pattern. Training patterns is in your hand. So it actually handles two classes, linear boundary between two classes. If you want to handle multiple classes, then you go for this NC2 combinations and take the pairwise things. Okay. So these are a couple of disadvantages of SVM. Be careful for that. Some more issues: choice of kernel parameter, and whether you want to go for a hard classifier or a soft classifier. It's very nice mathematically sound classifier rather than minimum distance classifier or neural classifier. But bottlenecks, yes, they're very sensitive to noisy patterns. They are linear classifiers. They are only for two classes. So all sorts of tweaking may be needed to solve your problem. You think of multi-class problem, you think of giving flexibility to submargins, or removing the noisy patterns, or solving a nonlinear problem. So all these are your choice. You need to go for this. Maybe I'll stop here. Thank you. Thank you so much for listening this talk for such a long time. If you have any specific questions, maybe I will try to give you a couple of answers to that. Else, I will stop here. Thank you. Thank you so much. Anybody has any?
Hello, sir. Good morning. I have a
Yeah,
doubt.
yeah. Please,
Actually,
please.
we were talking about soft margin, right, sir? Is
Mhm,
it
mhm.
incorporated with fuzzy membership function, or like soft clustering?
Yeah. So the softness or what you call slack variable, the amount of that slackness you can bring fuzziness. That could be a good way.
There is an echo. We are not able to hear you properly.
This amount of slackness, the introduction of slack variable, that zeta I have shown, the amount of that can be determined by fuzzy sets if you wish. That's possible. That could be a constant also, or that could be that we can have a kind of estimate of that using a kind of fuzzy set. Yes, that is possible. Incorporation of fuzzy set for that is possible.
Okay, sir. Thank you, sir.
Hello, sir.
Yes, sir.
Hello. Yes, sir. Please, I'm Victor. So you said something about how transforming non-linear SVM to a linear SVM or kind of stuff, sir. Yeah. So like, yeah, how is it done practically, sir? Like,
Yeah.
how do we
Okay.
go about doing it?
Not transforming the SVM, transforming
Okay.
the problem. Let us
Okay.
say the problem is non-linearly separable. What I mean is you have two classes, and these classes do not. I mean, in between these two classes, you cannot have a line. You have to have a non-linear boundary. Okay. Now, how do you solve this? If you want to solve this problem, then this problem you transform to another domain using kernel. The problem, the feature space you change to a new feature space such that the new feature space becomes linearly separable, and then you apply the SVM. So you are not changing the SVM. SVM is by its very nature linear classifier. What you are doing is you are transforming your original input space, original problem to a newer dimension using the kernel transfer function such that the problem is linearly separable in that space, and then apply the linear SVM. And that two together is what is called nonlinear SVM. Kernel followed by SVM. Kernel followed by SVM, or these two together inbuilt through some mathematical simplification. Now there is a question, how do I choose the right kernel? To be honest, there is no solution to this. That remains a research topic, and it depends upon your experience, in your expertise, your kind of experience working on this, and depending upon the problem. This is very much problem specific. There is no single word solution that okay, you use this kernel and you will get a solution. Absolutely, it's not available. This is a very big research topic, not yet solved.
Sir, one more question.
Please.
You are telling about kernel, right, sir? So the transformation, any transformation we can take or a kernel, because kernel will be an onto function, right? So
Yeah.
any transformation or a kernel is a must.
Kernel, only kernel functions. Not any transformation. Any transformation will not work because you have seen that in the expression of that SVM, there is an inner product x transpose y, y transpose x. So that is a kind of kernel property. So only kernels could be used for transformation that will simplify the job. Non-kernels cannot be used. So
Okay,
all transfer functions are not useful. Only those transfer functions which satisfy that kernel property, the Smart's theorem and this inner product property, they will be useful. Not all.
thank you, sir.
Any other from the audience? Ashish, good morning.
Morning.
Very wonderful talk. Awesome talk actually for everyone. So thank you very much for sparing so much time for us today. I know that you are all totally occupied and busy.
It's perfectly all right, TNN. No issues.
So, on behalf of my department and colleagues, I profusely thank Dr. Ashish Ghosh for enlightening all of you to the world of mathematics, world of features and support vector machines, taking you to the world of mathematical operations. So this course is basically uniquely designed to give you the complete mathematical operations of the techniques, starting from vector space to optimizations to statistics, and also some of the ideas in expectation, minimization, maximization. So all these things we have covered actually in detail to give you a strong foundations for those of you who are interested in conducting research in this area. So we believe that all these materials were really useful to most of you, and we look forward for your feedback to improve wherever there are possibilities, and continue to stay with this. I sincerely thank Dr. Ashish. Now that we can stop, actually, we'll resume again at 11:30 for the next talk. So thank you, Ashish. We'll catch up later on.
Sure. Okay. Thank you. Thank you. Thanks, everybody. Bye.
Thank you.